Hello learners, welcome to my channel RG Global Academy. In today's lecture, I'm going to talk about few error detection codes. For a computer network, data is transmitted from one computer to another computer, and there is a slight chance that data can be corrupted while transmitting through the noisy channel. Even in the same computer, when the data is stored in memory, there is a slight probability that data may be corrupted. So it is very important that the error is detected at the receiver side and sender protects the data and then only sends it to the receiver. So today I'm going to talk about simple parity check, vertical redundancy check, longitudinal redundancy check, checksum, and cyclic redundancy check codes. These codes vary from their ability to detect errors, and they are listed from weak code to strong code. And we are also going to learn about the few terminology in this field like encoder, decoder, Hamming distance, CRC polynomial, etc. So let's dive in. So data can be corrupted during transmission or in memory. And the solution for that is first detect the error and then correct it. In today's lecture, I'm only going to talk about error detection because correction is more complete. And for correction also we need detection. First of all, let's see types of error. The first one is single bit error. As shown in this figure, 8 bits of data is getting sent, and while transmitting it got corrupted and 1 bit is altered, and that is what is called single bit error. And the chance of single bit error is more than the other kind of error, which is called burst error, where multiple bits have changed and those multiple bits need not be consecutive. In this example, it is shown that 4 bits have changed, but their burst length, their span is 8 bits, which is called the burst length. So single bit error is more probable than the burst error. So there is a difference between error detection and correction. Error detection is simpler than error correction procedure, and we are doing only error detection in this lecture. So if the receiver detects error, receiver can discard the data and ask the sender to retransmit it. But for detecting error, the sender has to do something. The sender will append few redundant bits to the data word, and the whole thing together, data word and redundant bits together, is called a code word, and that code word will be sent to the receiver. Let's know about another term which is called block coding. In block coding, a group of data bits called the data word is protected by the redundant bits. Suppose the data word length is k bits, then r redundant bits are added. So total k plus r, which is equal to n, will be the length of the code words. So we are going to see today about vertical redundancy check, VRC code, longitudinal redundancy check, LRC, then checksum, and then cyclic redundancy check. And they are listed in order of their capability. Vertical redundancy check is the basic one, not capable of detecting all kinds of error. Longitudinal check is better, then checksum, and then the cyclic redundancy check. So to detect and correct errors, sender will send extra or redundant bits along with the data bits. So in the sender side, there is an encoder, and the job of the encoder is to take the data and feed it to a generator which will decide which redundant bits to add and how many bits to add, and then it will be the complete code word. So data and the redundant bits are also called check bits. They are together is the code word, and that is getting sent through noisy transmission line to the receiver. After the receiver receives the code word, it will send it to a checker, and check whether the data has been corrupted or not. If not, it will accept the data, and if corrupted, it will discard the data, and it may ask the sender to retransmit the data again. Let's see how the code words are generated in more detail. So if there is a data word which is k bits long, so with k bits there can be 2 to the power k data words, right? And each data word will be of k bits long. Now if r bits are added with that k bits, so the code word's length will be k plus r, which we are calling as n. So there could be 2 to the power n code words, but we need only 2 to the power k code words. So out of 2 to the power n possible code words, 2 to the power k code words are valid and others are invalid. Now the bit that will be added, the simple procedure is parity checking. Suppose we have a 6 bits of data which is shown here 0 1 1 1 0 0, and one extra bit will be added, and by doing a even parity checking, it will just count number of ones here, and here in this data there are 3 ones. So in even parity another one will be added, so that in the total code word there are even numbers of ones. There could be a odd parity scheme also. With odd parity scheme, because in the data word 3 ones are there, in a odd parity scheme 1 0 will be added to make even number of odd number of ones. So either even parity or odd parity is applied in a simple scheme. So I'm going to see another example where the data bits 2 bits data word length. So with 2 bits there could be 4 different data words 0 0 0 1 1 0 and 1 1. And one extra bit is added. Here you can see 0 0 and code word is 0 0 0. So it is applying even parity bit. And with 0 1 data, code word is 0 1 1, even parity. 1 0 1 0 1 1 1 1 1 0. This is the code word. So the data will be added with the redundant bit, code word will be generated, and that will be sent to the receiver. So upon receiving the data, what the receiver will do? Suppose the data sent was 0 1 1. After adding the redundant bit, 0 1 1 was sent. Now receiver knows that 0 1 1 is a valid code word, right? So receiver will accept it. But suppose receiver received 111. How is that possible? Receiver receives 111. Maybe these 0 bits got altered to 1. Then it will be 111. But then receiver will check the valid code words. 111 is not a valid code word. So receiver will discard this code word because the data is corrupted. So other terminology, let's go through them first, and then we are going to see how the number of check bits are determined. So in a data, the weight of the data, suppose I and j be n-bit binary code words, not the data, we are considering the complete code word, then weight of that code word is the number of ones in I. Wi or wj, that will be the weight, and distance of two code word dij is the number of bit position in which I and j are different. And in this coding system, it is important that the code words have more distance. More distance is better than less distance. Suppose here in this example, I is a code word. It is 8 bits long, 0 1 1 0 1 1 0 0. What is the weight of I? I is 4, and weight of j is 3, and you can check in how many bit position they are different. First bit position they are different, third bit position they are different, then this one fifth bit position they are different. So they are distance between these two code word is 3. Now we are going to know about another term which is called Hamming distance, and this is an important term. And Hamming distance means minimum distance between the code word, between the pair of code words. So you are generating 2 to the power k code words, right? So different code words have different amount of distance. So after calculating the distance between all pair of code words, you take the minimum distance, and that minimum distance is known as Hamming distance. Hamming, we are going to talking about Hamming code. Hamming is the one who has given all this error detection and correction code. So we are going to talk about him when we discuss the Hamming error correction code. But this term is very important, Hamming distance, which is the minimum distance between the code word. And depending on this distance, you can say how many errors can be corrected and how many errors can be detected. And let's see how many errors can be corrected and detected. And that is given by this formula, 2t plus s plus 1 has to be less than equal to d minimum. D minimum is the Hamming distance. So a code provides t error detection, t error correction, plus S error detection only. If and only if this following inequality is satisfied. Okay, let's put some numbers in there. So if we are looking for single error detection, which is also called SED, that means we are only looking for the S equal to 1 and we are not looking for correction, T equal to 0. So 1 plus 1 has to be less than equal to 2, right? So if D minimum is 2, then we can have only one error detection. Nothing more is possible. And if we are looking for single error correction, no extra detection, that means T equal to 1, S equal to 0. So D minimum between the pair of code words has to be 3. Similarly, single error correction and double error detection, that means S equal to 1, T equal to 1, T is 1 extra error detection, then D minimum has to be 4. So this Hamming distance is very important to know what is the Hamming distance in a set of code word, and accordingly the code will have error detection and error correction capability. That formula that we have seen in my previous slide, 2t plus s plus 1 less than equal to d minimum, can be depicted better pictorially. Suppose this circle is a valid code word and this is a valid code word. And just by altering one, you are getting a error word. So if that error happens, you know that error is there, but you do not know which way to correct it, to make this one to left code word or to the right code word. So if d minimum equal to 2, you can only do single error detection. No correction is possible. Now, if D minimum is 3, you will see valid code word. You change 1 bit, you reach here. You change 2 bits, you reach here. Then you change 3 bits, you reach to another valid code word. So in this situation, single error correction is possible. Suppose this is the error word. So you know that close valid code word is this. So you will be coming here, assuming that one error has happened. Similarly, if the error word is here, then you will be coming back to this valid code word. Or double error detection is possible. Either this you are detecting error, or if it is changed to this, you are detecting error. Similarly, here where D minimum is 4, single error correction and double error detection is possible. or triple error detection is possible. And when d minimum equal to 5, double error correction possible, or single error correction and double error detection is possible. Let's see our first error detection code, which is called Vertical Redundancy Check or VRC. It is based on simple parity appending to the information bit or the data word. So we already know what is the weight of the code, including parity and information bit. In odd parity code, there are odd number of ones, and in even parity code, there are even number of ones. So it can be created, VRC can be created either odd or even. In this example, it is shown even parity has been applied. So here you can see 7 bits of data, and 0 parity is getting added to the first data. Then second one is added, and like this. Okay, so sender is creating this code word, and now when the receiver is receiving, so suppose here one in the first code word, one bit has changed to 1. Okay, so this error will be detected easily by the receiver, because receiver is also calculating the even parity, and his calculation, receiver's calculation should have been the 1 parity, but what parity it has received is 0. So it knows that this data is corrupted. But suppose 2 bits have changed in the data, first data, then the parity is not changing, right? So receiver will recalculate parity, and parity is also matching. So receiver has no way of knowing that the data has changed and 2 bits have altered. So VRC is a very simple coding. 1 bit is added. It can check only single bit, or it can check odd number of errors, but it won't be able to check even number of errors. Let's see the second error detection code, which is called Longitudinal Redundancy Check or LRC. In this, a block of data words will be arranged in the form of rows in a table, and then same bit position from different data words will be given a even parity. Like here I have 4 data words are there, and here I am calculating the parity bits for this column. So 1 1 0 parity, then here second column has 3 ones, parity is becoming 1, and like this. So here you can see that I am using more number of parity bits. In the VRC, for 4 data words there will be 4 parity bits, but here you can see depending on the data length, which is here 7, I am using 7 parity bits in longitudinal redundancy check. So this will be also sent along with the 4 data words in a block. Now when receiver will receive the data, it is receiving data, it is receiving the sender computed LRC, and when the receiver is recomputing, if 1 bit is error it will find, but here 2 bits of error I will check. No, in the same data what 2 bits have altered, the second bit and the fourth bit. Here you see, here it was 1, here it was 0. So recomputed LRC will be different than the received LRC. So the receiver knows that error has happened. The third error detection code is called checksum. In this, a number of data words are added. Like here, I am showing those data words in decimal number for better understanding the whole procedure. So the first data word was 1, right? In binary, if I say it will be 0101. And 11 will be 1011, like that, but I have written in decimal. So 4 data words is a block of data words, and that are getting added. A sum is generated which is becoming 28. Now you know 28 cannot be represented in 4 bits, so this fifth bit is a carry. So that carry is again added to the sum, and now it is called the wrapped sum. And the wrapped sum is coming out to be 30. And then in the third step, the ones complement of that wrapped sum is taken, and that is called the checksum. Now, along with 4 data words, this checksum is getting transmitted. When the receiver will receive these 4 data words and the checksum, receiver will also add all of them, even the checksum. So receiver is adding 4 data words, 1 checksum. It got the sum 30. 30, this one was the carry, so it is also generating a wrapped sum, and that one's complement of the wrapped sum is generated, which is coming out to be 0, 0, 0, 0. So here the receiver is getting a checksum 0, and if the checksum is 0, receiver knows the data transmitted was good, no error happened. And if the checksum was not 0, receiver will know that error has taken place in the transmitted data, and receiver will discard the data. So in checksum error detection code, the sender side steps are, it is a block coding technique. So in the first step, it will divide the message into 16 bits data word. In the example, I have mentioned 4 bits for easy understanding, but actually the data words are bigger than that, either 16 bits or 32 bits, etc. So it is dividing the data into 16 bits data word. Then in the second step, it is summing all the data words. In the third step, it is adding the carry to the sum and creating a wrapped sum. And then the ones complement of the wrapped sum is called the checksum, that is step number 4. And then sender is sending all the data words plus checksum to the sender. Okay, just like what it is shown here. And in the receiver side steps are, it is again doing all the sums along with the checksum, and then it is also creating a wrapped sum just like the sender did, and then it is also taking one's complement and checking whether the checksum is 0 or not. If the checksum is 0, receiver accepts the data, otherwise it will reject it. Now our fourth error detection code is called Cyclic Redundancy Code. This is also a powerful error detection code used in Ethernet 802.11 ADSL cable. These are all computer networks protocol, and cyclic codes are called cyclic because if a code is cyclically rotated, it will get another code word. Like I will give example of the second code word here. Here 4 bits data word, right? With 4 bits there are 16 different data words, and all of them are getting some redundant bits added. I'm going to talk about how those redundant bits are added. But before that, I'll tell you why this is called cyclic. So I'm talking about this second code word 0001011. Now if you rotate it, then you are getting this code word for number 8. So from here to here you will get. Like that you can check that if you are rotate a code, you will get another code word. That's why it is called cyclic code word. And now data word is 4 bits long, 3 redundant bits are added. So total code word is 7. With 7 you can have 2 to the power 7. That means 128 code words, but all of them are not valid. Only 16 of them are valid. Now let's see how those redundant bits are added. So there is a key is needed for this code generation, and the key is also called the generator polynomial, and which is also called the divisor. Okay, so a 4 bits divisor has been taken, and then the data words, this is the data word, 4 bits data word, and because the divisor is 4 bits long, 4 minus 1, 3 redundant bits will be added with the data word. And so these zeros, 3 zeros are just the placeholder in the beginning. So this data word and these 3 zeros together will be divided by these 4 bits of divisor, and the remainder after the division is complete, 3 remainder bits will replace these 3 zeros placeholder. So code word will be generated, and that will be transmitted with the noisy transmission line, and in the receiver side it is getting the uh, code word, and this code word will again be divided with the same divisor. So the device sender and receiver both agree on a divisor or a key or a generator polynomial. They both know what is the divisor, and if it is getting a remainder, that is what is called a syndrome. And if the syndrome is all zeros, then it will accept it. And if the syndrome or the remainder at the receiver side is not zero, then it will discard it. So the whole procedure I will explain. So suppose I have a data 1100 and my divisor, which is also called the key or the generator polynomial, which is 1001. And my data is also 4 bits long, 1100, and because divisor is 4 bits, I am adding 3 bits with this number, okay, which I will divide. So now the total thing is 7 bits long, and I am dividing this. And when dividing, it is just we do subtraction, no? Right now, this subtraction is just a XORing. We are going to do XOR. This is called modulo 2 arithmetic. So we do XOR. So here after first we put it here, we do XOR. So I'm getting 101. I need 4 bits, so I'm bringing this 0 down here and then again dividing. The quotient is not important, so I'm not writing the quotient. And every time I'm XORing, and the beginning has to start with a 1. So with the 0 leading zeros, I'm not writing. And then you see at the end of the division, the remainder is 101. And this 101 becomes, instead of 3 zeros, I will replace them with 101. So the code word that will be sent is the data word 1100 and then 101. So what the receiver doing, receiver got this code word, and receiver knows what is the divisor or what is the key, and it is dividing it again. It got all zeros this time, and data is accepted. So this is the procedure. Sender will extend the k data bits with r zeros, and r is the number of bits in the divisor minus 1, and divide by the generator polynomial, that is the divisor, and keep remainder, ignore quotient, replace r check bits by remainder. And receiver side will do one thing, divide and check for 0 remainder. So that is the procedure for cyclic redundancy check. So here you can see when the data, that was the code word generated in the sender side, but data when got transmitted got corrupted. The 4th bit here was 0, here it became 1. So when the receiver is dividing this code word, it is getting a remainder 0, 1. And in this case, because the remainder is not 0, receiver knows that data is corrupt and this data will not be accepted. So this is the procedure. Now the question is how to select the divisor or the key or the generator polynomial. That depends on the data length. Data length will determine how big the polynomial will be, or it also depends on the Hamming distance. Look for a polynomial with a high Hamming distance to maximize the probability of detecting errors. Or choose a primitive polynomial for the best error detection. Choose a polynomial that is considered primitive. And then standardized options are also there. Some well-established CRC polynomials are there, like CRC 8, CRC 16, CRC 32, etc. And they have already proven to be effective. Like CRC 8 polynomial will be x to the power 8 plus x square plus x1 plus 1, which is actually 1, 0, 0, 0, 0, 0, 1, 1, 1, right? So this is the 9th bit, because power 8, 0 to 8, 9 bit. So x8 is there, so there is a 1 here. Then the next power is 2, so this one is 2. The next is 1 and this one. Similarly, for CRC 16, if this is the polynomial x16 plus x square plus 1, this is actually this big number with 17 bits. So today you have learned about 4 error detection code, and in my next lecture I will tell you what is Hamming code, Hamming error correction code.